And part 2 in our series on how to read vacuum tube electronic schematics. Hopefully you learned something in series 1. Do me a favor, if you learned something, post it in the either series, part 1, part 2, wherever you learn it at. Kind of post in the comments what you learned there. It would be helpful for me to kind of know how to focus this series going forward. And let's see here. Today we are going to cover power supplies. A few components, some tips, and then get into some power supply schematics. They're kind of foundational to everything. And then, in upcoming videos, I thought maybe we would do some push-pull amps and explain phase inverters. Thought maybe we'd do a couple more single-ended amps, maybe some preamps, phono stages. Maybe just hit a little bit on push-pull parallel or single-ended parallel. Thought I would do a couple guitar amps throughout this series, and then thought I'd hit some of the classics, the Fisher 500C, Western Electric 91, Citation 2, Dynaco ST70. You get the idea. If there's something you really would like to see, like a schematic you've been racking your brain on and would like for me to cover it here, I sure could. So make a post about it and I'll try to add it to the series. All right, just a few more tips. I mentioned this last time. It was kind of the eating an elephant statement, but break the circuits down into the sections by what they do, and I'll show you that here in today's video. Be sure to use your parts list or bill of material to help identify components. So if you see something on there, say R27, and you're going, not really sure what the value of that should be or what it is, a lot of times the parts list may tell you exactly what that is. It may say something like grid resistor or coupling capacitor or something. It may help you identify it by looking in the parts list. Kind of look up components, find their data sheet, research all aspects of it. It's easy to, I'll give you an example. Let's say you're trying to figure out the wiring on a Fisher 500C output transformer. You're looking at the schematic and it's just not clear to you. You could always Google Fisher 500C output transformer, probably find somebody that's remanufactured one and see a schematic diagram of that, and probably tell you about the voltages and different things that maybe the schematic wouldn't. If you don't know something in a schematic, or what it does, ask someone. Don't assume, don't be ashamed. It's what this hobby is all about. It's sharing and learning, and shoot, I ask a lot of questions myself. I make a lot of posts on Audio Karma, and I'll say, hey, I'm working on this. Ran across this. I'm trying to figure out exactly what its purpose is here, because sometimes circuits get pretty tricky. So don't be ashamed. Good schematics have voltage references on them, and I'm going to show you an example of a good schematic here in a minute. But if yours doesn't and your unit's working, you could always measure at various points and mark up your schematic yourself and put your own voltage references on it. 1 second here. Had to catch my wind before I got into this one here. It is possible to build something using a schematic as your guide, but never understand what the schematic or the components you're putting in there actually do. And that's one of my beefs with the industry, not just today, but over time. A great example is Bottlehead. I've probably built 20 or more Bottlehead units over time. I really think it's good stuff. The downside, they don't even provide you a schematic. All they provide you is a set of instructions on how to build this amplifier. So it's more of a solder this to that and attach this here and there and run this wire from point A to point B. But it never tells you what the components are. It never says, hey, this thing you're connecting right now is a diode that we're using for the cathode bias in lieu of a resistor. It doesn't tell you that kind of stuff. It just says connect this thing from here to here. And so it really aggravates me. Same, even back with the older Dynaco stuff, the ST70, the Mark IIIs, whatever. They did a much better job of telling you, kind of giving you a schematic. But no, I have yet to see an amplifier with something that actually walked you through what all the components actually did. So you could actually learn more than building techniques. You could actually learn the electronics and what's going on behind it. So if I ever, retire one day and build a kit, it will come with instructions that walk you through from beginning in, not only how to build it, but also what each component does and its function in the circuit. And then again, I'm going to hit this one more time. The only way to get good at this stuff is spend time doing it, keep doing it, ask more questions. I promise over time these things will start to become just like reading a street map. You'll totally understand how to read one. Okay, back in the day there was a company called Sam's that made these things called Photofacts. And basically what they did was they took an existing piece of gear that the manufacturer put out on the market, and they then took their factory schematic and enhanced it greatly and put together a whole booklet telling how to troubleshoot, common failure points, things you could modify to make it better, things of that nature. And so this is a great example of a schematic from a Sam's Photofact. So they kind of took, I think this was some kind of radio, but it's got a 6BQ5 output in it here. But you'll notice here what they did up here on the grid of this 6BQ5. They tell you that there is minus 15 volts sitting there. They tell you that on the plate there's 190 volts. They tell you that here on the screen there's 185 volts. And they tell you that here on the cathode there's 10 volts. So you actually understand how this tube is biased. And then you could, if you had this actual radio on your bench, you could then go in there with a voltmeter, DC voltmeter, and you could measure these voltages. And if you don't have those voltages listed right there, then you would know something's out of whack, and you'd kind of have an indicator of where to start chasing it down at. So Sam's Photofacts were just absolutely great. You can see here it tells you there's 205 volts AC. Tells you over here there's 205 volts at this point. Did a really good job of breaking voltages down on circuits. So in my book, a grade A schematic has voltages indicated on it. Okay, before we get into a couple of example schematics, let's go through a few more kind of symbols that I commonly see used out there. First one up here, you see this one, the most common. It is a SPST, otherwise known as single pole, single throw. In other words, it has one little wiper inside the switch that's either open or closed here. So that's single pole, one pole, and single throw, either open or closed. There's such thing as a single pole dual throw, which means it's one wiper here, and it could either be connected to this pole or this pole. In this scenario, here's one DP, dual pole single throw. In other words, when you throw it, both switches either open or close at the same time. And you may see this in some kind of circuit that lets the left and right channel through. Then you got dual post dual throw, so it could be feeding to the left, could be feeding to the right. This is pretty common right here to see in your car. You probably touch one of these all the time. That is what would move your windows up or down. So if you flipped it one way, it would provide connectivity for the window to go down, and if you flipped it the other way, it would provide different voltage to different poles to pull the motor downward. This is a push button switch, so this one is called a make switch. So it's open until you push it and then it goes closed. In other words, you push it to make the circuit connect. Or this one, you push the button to break the circuit, so it's normally closed, as we call it. You push the button and it opens the circuit. This one would kind of go from connecting one set of wires to another set of wires. A rotary switch, so as you turn the switch it may connect different switches here onto different poles. This is very common to see. A great example would be the selector switch. So in other words, your input comes in maybe from 4 or 5 different sources. Maybe one of these is from CD, maybe one's from the phono, maybe one's from the aux, maybe one's from the FM tuner. And as you flip this switch, it would determine which source it's going to get its audio from and then send it on to the rest of the amplifier. As you can see over here, the normally closed, normally open nomenclature is something you should get used to. It just means without pushing the button or flipping the switch, what is it normally doing? It's either normally closed or open. And you can see a kind of a step ladder here of single post, single throw, single post, dual throw, dual post, single throw, dual post, dual throw, and a 4-post dual throw. You see a lot of this in maybe band switching or whatnot in a HF amplifier. Okay, another common component seen in amplifiers, specifically the power supply units, which we're going to be talking about today, are these things called chokes. Chokes are nothing more than a very large inductor. typically with some type of iron core inside of it. This is a very common style of choke right here, the Hammond series. I use a lot of the 10 or 8 Henry at either 75 or 100 milliamps and things that I'm building. And what you've got here is you've got an iron core inside of this bobbin, and this bobbin looks kind of like this thing over here. It's nothing more than a wire going in one end, wound around this plastic core, and then coming out the other end, and then inserted inside of that plastic core is some type of ferrite core here, which is kind of what you see, the black around the outside of these. This one actually uses what's called an EI frame, and so you've got this E-shaped ferrite core here that goes around, and then an I shape that goes across the top. And so you kind of imagine this little bobbin here stuck on the middle part of one of these. And a couple symbols for that, just plain old inductor, typically an air core, nothing in the middle here would be this symbol, an inductor with a ferrite core. So this is ferrite here, and what that is it's a basically ground up ferrite shavings or powder that's then been kind of glued together to form a stick. And that's what you'll see, these little broken lines. And if you're using something with an iron core, in other words, metal laminates of iron, a lot of times these E and I shapes are little metal laminates. They'll have a little solid indicator on them. So these would be the symbols. This bottom would be the symbol for what you're seeing right here. Okay, a couple slides here on transformers. First and foremost, let's start at the top here. Typical transformer has what's called a primary and a secondary, like down here in this picture. In other words, you feed a signal in an AC signal. Transformers are AC devices. They do little of nothing except get hot if you feed them with DC. So you feed them with an alternating circuit, which current, which could be 160 hertz coming out of your wall outlet for a power supply, or it could be your audio signal coming out of your output transformer in the case of coming out of your output tubes in the case of an output transformer. But the goal here is to take a AC signal on the primary, and then you have electrically disconnected it through this gap here. But you're picking it up via a magnetic induction into the secondary, and typically you have a different number of turns in the primary than you do in the secondary, and what that does is it does some type of impedance transformation and or voltage transformation. So in the case of a power transformer, you may feed 120 volts in here at 60 hertz, and on the output here you may want to get 400 volts at 60 hertz to feed a high voltage section of your power supply. Just a few more symbols. Typically a transformer with an air core looks like this, one with a ferrite core looks like this, and one with an iron core looks like this with the double bars. And one last thing on transformers, they could have 2 wires going in as the primary and 2 wires coming out as the secondary. There's also something called a center tap or a tapped transformer, and that's where your primary may feed in with 2 wires, but your output may be center tapped. In other words, a third tap coming off the center here. What you can actually do with that is, let's say, feed 120 volts in but get 300 volts out. Well, if you measured the voltage from here to here, you'd actually have 150 volts here, and if you measured the voltage from here, you'd have 150 volts here. But if you measured from here to here, you would have 300 volts of AC at that point. Okay, if you're going to get good at reading tube gear schematics, you're going to have to understand transformer taps. So I got a note up here that says taps are just points on the winding where you pull off voltages that are actually less than the total end-to-end winding provides. So let me give you a good example here. This is a Fender Deluxe power transformer made by a company called Classic Tone. They make reproduction transformers in case your classic guitar amp dies, power transformer burns up in it, you could go buy a replacement. But you can see here it has a white wire and a black wire for the 120 volt 60 cycle primary. And then this is a great example. If you go from red, what's labeled 6 here, to number 3 here, what you end up with is 660 volts from red to red here. But then if you came over here and got on the center tap, which is number 4, which would be a red and yellow wire, it'll tell you that it's center tap, so that's half of the full voltage. So 660 divided by 2 would be 330 volts. And then what it tells you here, that if you go from the red, yellow to the blue, in other words, from the center tap, which often in a power transformer gets grounded, by the way, if you went from that ground point to this point right here, this blue wire, which is the bias for the cathode on the 6V6 outputs on this amplifier, or 6L6, I can't remember which one, but it would provide you with 50 volts of AC by going between number 4 here and number 5 right here. And all it is a tap so far away on the winding that it would produce 50 volts from the center to there. Then you'll notice you've got 2 taps here that are green. They are providing 6.3 volts at 3 amps. So take a guess at what those feed. That's right, they feed the filaments. And then you've got 2 more wires, yellow and yellow here, that provide 5 volts at 3 amps. Well, take a guess what that feeds. Yep, if you said the filaments for the rectifier, you are correct. And this would be go to like your 5U4, 5V4, 5AR4 type tube. And this would go to your 6-volt tube, so a 6SN7, 6SL7, maybe you're feeding a 12AX7, but you're using that center tap we talked about yesterday. So that's a classic tone transformer. This is an ED-core power transformer that I use a lot of when building amplifiers. It feeds in 120 volts on 2 wires. Then you've got 360 volts, 360 volts in center tap. Well, 360 and 360 is really 720. So you see 2 different nomenclatures here. This one tells you it's 660 volts with a center tap. This one actually tells you the voltage of each wire, and then it shows you have a center tap. So if you were to write this one the same way as this one, it would be written 720 volts center tapped. Here you've got a 60 volt orange for a bias of your grid somewhere. Here you have 6.3 volts for your filaments, and then again 5 volts for your filaments here. So very similar transformers, just written a little bit differently. We're going to spend a few minutes talking about single-ended output transformers because they're a little bit of a special creature. If single-ended output, what that really means is an amplifier that has been biased in the Class A configuration, in other words, a Class A amplifier. If you do a little bit of studying on Class A amplifiers, what you find is that the output tube or output device is biased on 100% of the time, conducting 100% of the time. In other words, you could think of that as a 100% duty cycle. And that because the tube is conducting 100% of the time, so is the output transformer, and that creates a little problem for these output transformers. As you can see here, this is a cross-sectional view of a single-ended output transformer, and you have the little E section here of the core and an I section here of the. And typically these are thin little iron laminations, and they're stacked on top of each other to kind of make this look. And if you did a cross-sectional view, this is what it would look like. But basically what happens, because this thing is conducting 100% of the time, the eddy currents that flow inside the transformer here, basically magnetic currents that are flow in the core, they're flowing 100% of the time, and what it causes is a phenomenon called core saturation, where basically the magnetic permeability of the core here starts to saturate, and ultimately it causes the transformer to get hot and overheat. And so you can kind of stop that phenomenon by breaking, giving an air gap here in between one of the poles of the transformer, so that these currents can't constantly flow. Sometimes you'll see an air gap on one of the poles, sometimes you'll see an air gap on all 3 of the poles, but regardless they have the same purpose, is to keep that core from saturating, which can cause distortion and then ultimately heat and the transformer overheating. You don't see this phenomenon in push-pull amplifiers because the way they're biased, the output tubes are only on 50% of the time, or thereabouts 50% of the time. And while then it switches over to the, let's say that was the push part, it switches over to the pull part, and the other tube conducts while this this tube is cooling down a little bit, and the same goes with the output transformer. It has opportunity to cool down and not saturate because it's only conducting 50% of the time. So that's why we've got to have this air gap in a single-ended output transformer. Okay, I'm gonna get a little bit techie with you here for a minute, so hang with me. This is a single-ended output transformer little diagram or symbol from EdCore. And I was just going to talk about it looks pretty simple, but there's a lot going on here. Let's talk about that. First and foremost, I need you to recognize that there is a difference between the primary impedance of this transformer and what would be known as the DC resistance on this side. So in other words, if you hooked a lead to this red wire and another lead of your DC ohm meter to this blue wire and measured it, you might see about 150 or 160 ohms of DC resistance. And you're sitting there going, well, this thing says it's a 5,000 ohm primary. Well, that's 5,000 ohms of impedance, not 5,000 ohms of DC resistance. Those are two very different things. And you may want to read up on the difference between the two. DC is kind of measured at DC. Impedance is typically measured at a frequency, and the frequency plays a role in the impedance. So typically you'd measure that at a kilohertz or 10 kilohertz or something to get the 5,000 ohm resistance that is on this thing. Similarly, you may measure 70 ohms if you measure the orange wire to the white wire here, and you'll say, well, wow, this is supposed to be an 8 ohm output transformer, not 70 ohms. Well, if you measure the impedance of it, it would tell you that it is at 8 ohms. And then there's a ratio between these two. So this might be 5,000 ohms primary and 8 ohms secondary. And the reason you need that transformation that happens in this transformer is that your output tubes operate best at a load of, say, in this case, 5,000 ohms. Your output tubes would not operate if you connected the outputs of your speaker wires directly to it and tried to load it down with 8 ohms. So that's why you need this inductance transformation. The other thing that you notice here is that this thing has a tap in the middle of it right here, a white and blue tap, and it's labeled screen. Okay, so a couple things here. Let's pretend that the output tube we're using is a triode. A 2A3, a 45, a 300B, something along that line. There is no screen to connect to in a triode. Remember, triode, cathode, grid, plate. There is no screen. So you would simply cut this wire off, maybe leave some room there because you might want to use it later, but you would kind of shrink wrap the end of it or something to keep it from being utilized, and you just use the same transformer without using the screen wire. So if you're looking for a output transformer for a triode, don't be afraid to buy one that has a screen tap. You just won't use that portion of it. Okay, remember, even though we're feeding the B+ through this output winding to the plate of the tube, as that tube is turned on or off, it turns on or off here how much of this plate voltage is conducting through here, and the turning on and off of that is what is it is equivalent to the audio output, because the variation in the grid ultimately turns on or off the current flowing through the plate, which ultimately ends up being your amplified audio signal. So from the B+ here to the plate lead here, that is a big swing of voltage matching your audio signal. Well, the purpose of this screen tap is to take a portion of that and feed it back into the output tube onto the screen. It's a form of feedback mechanism to the tube. And if you'll remember, feedback always does a really good job of kind of one, it helps lower the output impedance of that tube. Two, distortion numbers get lower. Power output can be higher. Good things that can happen from feedback. Some people will say, you know, as a purist, that it maybe doesn't represent the signal quite as well as an amplifier that doesn't have feedback, and that's why sometimes people would say a triode amplifier is the most true to the actual audio source. But this phenomenon here, where you're feeding some of the screen tap back to the output tube in a form of feedback, is known as ultralinear operation. That's a very savvy word. And typically this screen tap is at a percentage of the overall output. And you know, for a lot of tubes like a KT88, EL34, this thing's typically at around 40 to 43%. 43 is a very common number. Like if you looked up this Ed core transformer, it would tell you this screen tap was 43% of the overall amount of the circuit here. And other tubes like a a 6V6 and some others, they like a percentage more around 20%. And I'm trying to think, like leak amplifiers, they use around 50% on their taps here. So some people have done some tuning over time and trying different things that that work best for them. But sometimes you'll see an amplifier that says it has a flip switch that either turns it into triode operation or ultralinear operation. And what the difference would be is flipping between using this screen wire, or maybe actually connecting the screen of the tube to the plate of the tube, which kind of turns the tube into a triode at that point. And so some amplifiers have a little flip switch that you can go back and forth between those, and it does alter the sound somewhat. And last but not least, down here is a Hammond single-ended output transformer. You'll notice has the two taps here, and it has a screen tap here, and this one happens to be at 40%. And then it also here has, check out this is different. Like this up here has you can pick when you order this Ed core transformer either an 8 ohm output, 4 ohm output, 16 ohm output, but it has a fixed output. So whatever, if you built that amplifier, that output would be fixed. And let's say you buy the 8 ohm version, but then you know, a buddy comes over and he's like, hey, I bought these new speakers, check them out, and they are 16 ohm speakers. And you're like, wow, can't hook it up to this because I've only got an 8 ohm output on this thing. But some transformers have multiple taps on them, so black is kind of your common. And then you could feed multiple output taps on your amplifier, one for 16 ohms, one for 8 ohms, one for 4 ohms. And you would just hook the negative wire of your speakers up here to this black one, and then depending upon the output impedance of your speaker, let's say they were 16 ohms, you would connect the other wire here. And when your buddy leaves and you go to hook your speakers back up, you connect them here to the black common and to the 8 ohms. So it's neat sometimes to have output transformers that have multiple taps for the secondary here. And these, just like over here, these are at some percentage of the overall winding that would tell you, that would get them to 8, 4, and 16 ohm. Keep in mind, if you had an output transformer that wasn't labeled and you were trying to figure out which wires were which on it, you could always use your DC voltmeter and measure DC voltage across this, and your 4 ohms would have less resistance than your 8, which would have less resistance than your 16. But it's not going to tell you 4, 8, and 16. It might say 40 ohms, 60 ohms, 80 ohms, but you just have to translate that to 4, 8, 16. Okay, in a push-pull amplifier where you have 2 tubes and they're biased in a configuration and the output so that each tube is on about 50% of the time, handling the load of the output, one handling the positive cycles and the other handling the negative cycles. Typically that's called either Class B or Class AB configuration. And in that case, what's happening here is you're feeding one of the tubes here on this half of the transformer on the primary. You're feeding the other tube on this half of the transformer here, and each side, like before, has a screen tap. So basically you're feeding one output tube here and one output tube up here, each that conduct about 50% of the time, and just like before you have a single secondary output here on this thing. And then this one shows where you would have a Hammond here, where you would have the same thing, you know, one output tube connected here, with a screen tap, another output tube connected here with a screen tap, but you have multiple secondary taps here like we talked about before. Okay, one more thing about transformers. Could be output, could be power, could be any type of transformer. But there's something called phasing in a transformer. And I'll give you an example over here. This is a really good one. Typically, transformers will have dots on them, and sometimes they don't. But it just kind of tells how the secondary is connected to the primary. I'll give you an example. This one, let's say the windings all go right hand here, and they all go left hand here, and right hand here, and these might go right hand here, causing the secondary to kind of be flipped from the input. So here's an example. These have the primary and secondary voltages in phase. In other words, as this one goes up and down and then back up, this one goes up and down and back up. But in this one, you can see here the windings are actually flipped, so that as this one's going up, this one's going down, the output's going down, and as this output's coming back up, this one's going down. So this is known as these are 180 degrees out of phase, and you can see here if these two dots are not aligned, then these mean these are 180 degrees out of phase. Similarly, up down, this one's going down up. Just something to be aware of. You don't run into it an awful lot, but it is something you need to know about transformers. And on the symbolism here, that's what the dots stand for. Okay, before we dive into our first example, I thought I would show you how you kind of take an amplifier and break it down. So this is a classic Dynaco Mark III 60 watt push-pull amplifier, and typically these are mono blocks, so you would have a complete power supply, driver output, all of that for one amplifier, and you'd have a complete all this duplicated in another chassis, and you would feed your left audio into one, your right audio into the other, and that's what you would call monoblocks. But I've kind of taken some color coding here and I've broken this thing down a little bit. Hey, down here in the blue on this schematic is the power supply, and so basically where I stopped at with my blue line is where we were leaving the power supply components and they were just becoming feeds to the rest of the amplifier. Up here you would have what you would call maybe your input or your driver stage. Depending on the amplifier, it may have a phono section, may not. It may just have a preamp section. You could call this the preamp driver. And then over here you kind of have your output. And the way I kind of just differentiated these two was I started with the input and I started working my way through the stages here. That you got two gain stages here. Well, one gain stage and one phase splitter. And then you get to these coupling caps right here that kind of separate these stages from the final output tubes here. So that's why I broke the line there. And then right on the other side of those capacitors here, you would have what would be known as the output section, your KT88s here. And then that would feed into the output transformer, so on and so forth. But the reason I wanted to break that down is today's video is focused on the power supply. So we're going to walk you through a couple power supplies today, and then we'll kind of in upcoming videos talk about some of these other sections. Alright, so let's use this Dynaco Mark III as our circuit example number 2. Let's walk through the power supply here. I always, just like on any amplifier, I start on the left and kind of go to the right typically. And I'll start with the input for a power supply, which happens to be your power from the wall. And here you have 117 volts, and this little symbol here indicates the wall plug, and it'll tell you it's at 60 hertz here. That's what that little symbol stands for, 60 cycles, otherwise known as 60 hertz, 60 times a second. Then you come off of one leg of the power cord feeding after it gets inside the amplifier chassis, and you put a switch here. So this is a single post, single throw switch. In other words, open would mean off, closed would mean on, because then it would be making connection and it would feed the primary of this transformer. On the other leg of the power cord here inside the amplifier, they have fed this little symbol here with two dots on the end, and a little squiggly line is a symbol for a fuse, and it'll tell you it's a 3-amp fuse. In other words, if something goes bad in this circuit or the power supply, or maybe one of these tube shorts or whatnot, and all of a sudden you've got a short on the other side of the power supply and it starts drawing more than 3 amps, this fuse would blow and open up, and basically from that point kill everything else in the amplifier, because you would have no power going to the primary winding of your transformer right here. Okay, then this power transformer has a couple different taps on it. Let's start up here at the top. First, you've got these windings that come off right here that feed to, if you notice here, 6.3 volts, and that has a center tap to it that's tied through this capacitor over here to ground. So in other words, you know, if you measured across number 1 and number 2 right here, you would have 6.3 volts coming out of this, and the center tap ties it to ground. In other words, this these things are 6.3 volts sitting at ground level. You could use that tap to float these 6.3 volts at a higher voltage than ground, and this is AC at this point, so you're going to actually feed your filaments on this amplifier with alternating current here. And then you've also got another transformer. This is the actual power windings here in the middle, and if you'll notice, you have a center tap here that goes to ground, and one side of it goes off to the plate here of a GZ34, otherwise known as a 5AR4 tube, and the other side of this transformer goes to the second plate in this tube. And what this creates is a dual section, dual diode rectifier here, basically. And if you'll notice, then there's also another tap here a little far away from ground, but not all the way up here. So what this is, and we talked about it before, this is where you pull off a bias tap right here. And if you'll notice, it's just going through a diode, which then feeds over through a capacitor to ground to help filter. This is a filter capacitor at this point, helping filter off some of the ripple that would exist after this diode, because remember, right, this is a single diode rectification at this point. In other words, known as half-wave rectification. You need to go look that up. Look up half-wave rectification, and this tube here, because it has two basically diodes in it, is full-wave rectification. And then you've got these resistors here and a nice little tap on this 100K ohm resistor and this 18K going to ground. In other words, this is just a voltage divider setup that lets you adjust the bias feeding into these output tubes based on how you would turn this potentiometer right here. Okay, up next you've got the 5-volt winding here that feeds pins 2 and 8 of this GZ34, otherwise known as a 5AR4 rectifier tube. And the GZ34 is a kind of a unique little animal. Even though the you feed pins 2 and 8, it is somewhat treated as an indirectly heated cathode, because the filaments are physically separate from the cathode here. In other words, these wires get hot and heat up the cathode. But unlike an indirectly heated cathode, the cathode is electrically connected to the filaments, which makes it a directly heated cathode in electrical senses. And so you could theoretically swap out this GZ34 with like a 5U4 or a 5V4, where the cathodes were directly heated, and this amp would likely still work, maybe at slightly lower voltages. But you got an interesting phenomenon here where you have the high voltage being fed into this transformer, going to the plates of these tubes. This thing's conducting, it's going to the cathode here, which is causing rectification, full wave rectification here. And what you end up with on the output here is 480, 500 volts sitting right here. And you're saying, well, whoa, I don't understand that. There's 500 volts sitting here, but you told me you were feeding it with 5 volts. Well, that's 5 volts AC, which would be superimposed on top of that 500 volts DC sitting right here. So you can mix and match DC and AC by superimposing them on top of each other. So coming off of this, you would have a kind of a Ripley signal. You would have the rippled signal from the rectification, plus you would have this 5 volts AC sitting on it. And then that's the purpose of this next section here, which is the power supply filter circuit. And in this case, it is a CLC filter. And you might say, what does that mean? Well, this is a capacitor, remember, and because it's got a straight line and a curved line here, that is an electrolytic capacitor. In other words, it's polarized. So you got a capacitor, and then this symbol here, if you'll remember it from the other day, it's got 2 bars on it. It shows it's an iron core inductor. So C, and the symbol, electrical symbol for a capacitor is C. The notation for an inductor is L, and this is another capacitor. This is, you can see it's polarized because one edge is curved and the other side is flat. The flat side will always be the positive side, and this is a 20 microfarad / and what that tells you at 525 volts. 30 microfarad. If it doesn't have the UF, you just assume it means microfarad, and at 525 volts. And they don't actually here on this schematic tell you the value of this inductor, but I think if you look up this choke online, you would actually find that it is about a 1.75 Henry at 200 milliamp choke. And if you measure the DC resistance from one end of this to the other, it's about 62 ohms you would find. The CLC filter does a really good job of filtering out all that ripple on one side of this, so that on the other side over here you have a flat, solid 480 volts, otherwise known as the B+. And notice where this thing feeds. It goes upwards here, and it goes into the center tap of this push-pull transformer. And if you remember back a couple of our push-pull transformer pictures, it showed the B+ going to the center wire there. And you may wonder, well, what is this little thing over here? Well, what this is you're using this 680 volts to drop it down here to another level that ultimately feeds into another tag point in this amplifier. And I was trying to find where tag point number 5 is, and I'm not seeing it, but you can see it feeds off here at another point. Notice there's a little dot, and it feeds up here, and that's how you're feeding the plate of this next tube. So you're taking this 480 volts B+ here, feeding it over up through a resistor here into the plate of this tube, and because you've dropped the voltage through these 2 resistors, what you may be feeding on the top of this tube right here may be more like 300 volts instead of 480 volts. And if you feed on down this line, you'll notice another connection here goes through a couple more resistors here, some that are feeding the screen here, that's how you get your screen bias right here, and feeding on up and going to the plate of this tube even at another lower voltage because of the 2 drops happening here. So you use the B+, what they'll call the power rail, to feed multiple points in an amplifier, and you change the voltage you need for those multiple points by using resistors to drop the voltage to what level you need. Now let's say this tube needed 600 volts. You couldn't get there. If this thing only has 480 here, there's nothing you're going to do to ever increase the voltage, but you can decrease it through using dropping resistors. Just a few more symbols here before we leave circuit example number 2. Notice down here it says printed circuit eyelet. In other words, the Dynaco Mark III has a couple printed circuit board on it, and this little symbol here is for a circle eyelet. In other words, a connection point on that board where you would solder a wire to. So the wire coming from the power supply here does 2 things. One, it comes up here and feeds this transformer, but it also there's a connection from that wire that goes over here through a 6800 ohm resistor into point number 5 on this circuit board, and that's what that is symbolizing right there. So it's a little bit of a physical connection here being shown on a logical circuit diagram. And on to circuit example number 3 here. It is a Fender Deluxe Reverb, such a classic amplifier. In this case, let's take and walk through it the same way. This is not the whole schematic. I kind of cut out the section tied to the power supply here. But you can see you've got your AC outlet jack here. Plugs into the wall, and then feeding in parallel with that, if you'll notice it's tagged here and you'll see the symbol that's being used, that's an AC receptacle, and you're wondering what the heck is that? Well, some amplifiers on the back of them, in parallel with the input cord here, they'll just tap another outlet or receptacle there, so you could actually plug another device into the back of this amp. to keep from losing a power outlet by using the amp. You see that sometimes on hi-fi preamps. They'll have a couple spaces in the back that's just in parallel with the power cord for using to be able to maybe plug your turntable in or CD player, things of that nature. If you'll notice, we're feeding over here then, and we tag into a slow blow fuse here. So you might say, oh, what does that slow blow mean? Well, there's a couple different kind of fuses out there. There's fast blow, there's regular, and there is slow blow. And fast, at the slightest little hint of any transient above 1 amp, that thing would blow. I mean, just like instantly. A regular fuse might take just a little bit of time, maybe a few microseconds, milliseconds instead of microseconds, and then the fuse would blow. And a slow blow might wait a whole second or so before blowing. And what that does is it lets you run with a closer tolerance fuse to the actual circuit current being pulled, and it also keeps from when you power the amp on and you get all this transient surge of power being pulled at that instantaneous moment, or the voltage spike pulling current. It would protect against that, so the fuse wouldn't blow. Otherwise, you may need a 2 amp fuse in there just to keep it from blowing when turning on. But then your amplifier is operating with a fuse in it a little bigger than it needs for the actual circuit during normal operation. So slow blow fuses kind of take care of that. And then you notice you got a switch up here, single pole, single throw. When it's closed, the amplifier comes on because you're completing the circuit loop here, letting AC flow into the primary of the transformer. When you open that, you break the circuit, doesn't flow, and the amplifier turns off. And then you're wondering, well, what is this little thing right here? It's a switch, a single post, single throw switch that flips between one side of the power cord and the other side of the power cord. And then it has a capacitor here. If you'll notice, it's 0.047 at 600 volts. And that's a symbol for ground turned sideways. So capacitor tied to ground between the switch. Well, this is forever been known now as the death capacitor right here. And what it's doing is it's basically tying an AC ground, not DC, because this capacitor would block DC, but it's tying an AC ground, or one leg of this thing or the other back to ground from an AC standpoint. And what that's used for is to get rid of hum in an amplifier. Remember the old 2-prong plugs like this? Some of them didn't have a polarity on them. So if you're using that in a house that is actually wired with polarity on one or the other, flipping this switch to one side or the other may help reduce the amount of noise or hum in the amplifier coming from the power supply. The reason this thing's called a death capacitor is when this thing actually shorts right here, if you'll notice, you're before the power, the fuses or whatnot, so you end up with your little AC signal going straight to ground at that point, and could actually cause a short, and if you happen to be connected to this in any way, would not be good for you because you'd not be protected by this fuse. Okay, up next you see this the secondary of this transformer here, and hey, it shows you two things here, two secondaries that are going to the GZ34, 330 volts on each side, otherwise known as what 330 and 330 would be 660 volt with a center tap, and the center tap here is grounded. And you notice this winding here, and it's going over here to the filaments of this. So guess what that winding is? You're right, it's a 5-volt winding. And this says to all the 6.3 volt heaters, and then you notice the center is grounded here. So even though all these wires here or taps aren't labeled, you can start to kind of figure out what they are. And I took a picture of I think this is it's a replacement transformer for a Fender Deluxe Reverb that I found, and you can kind of see 660 volt center tap, 120 milliamps. There's also a bias tap, which would be this one right here, feeding up through that. There again, single diode, a filter capacitor here, then feeding in, going up, and biasing. So this is a guitar amp, same exact circuit you just saw here that you did in the Hi-Fi Mark III amplifier as it came to pulling a bias tap off and how they rectified that. And then it shows, you know, you got your center tap here, your two green ones, which would be these two down here. And it shows on this one no center tap. So for whatever reason they didn't show it. I'm betting it probably has it. But if it doesn't, it's fine because you're tying that thing to ground anyway. And if you don't put a center tap on it, it's basically going to be at ground. And then the two 5 volts here at 3 amps to light up the GZ34. Just like on the GZ34, you're also pulling off here your B+. So this is going to be feeding up to go to your power tubes. And if you notice, it has a little switch right here in the line called the standby switch. And what that does is it actually lets your tubes get the voltage from the filament winding here. Let your tubes warm up before you ever flip the switch on here and actually apply B+ to the tubes. Or if you're just standing there and you know, playing your guitar and you want to kind of shut the guitar off, the amplifier, so it's not making any noise, not picking up anything from your guitar, but you don't want to turn the whole amp off because you don't want to have to wait on the tubes to warm up and whatnot. Again, you can flip this standby switch, and that's what that does. So that's pretty much the power supply for a Fender Deluxe Reverb. Not much different at all, with the exception of this little death capacitor setup here and the ground switch than the Mark III Dynaco hi-fi amp. And circuit example number 4 here, we'll go back to that Michael Adela KT88 amplifier I showed you in the previous one, and this is the power supply for it. So it's a little more of a modern schematic here. If you'll notice here, you've got kind of a modern IAC connector, so it would show you how you would wire this thing up, and you've actually got the amplifier chassis grounded here, and then you kind of got your neutral line here where you'd put your power switch, and then your hot wire here where you would put your 1 amp fuse, and it would feed in here to the power transformer there, again feeding the plates of this 5U4, and then you would you know, take the 5 volt AC, feed this 5U4, and just like before, then you pull the high voltage B+ off of this, send it over through a standby switch like we discussed before. Then we got another CLC filter here, and so you got your capacitor, your 10 Henry Hammond choke here, another capacitor here. This one's 10 microfarad Solene, and if you notice, this is just straight and straight 630 volts. He's using a kind of a polycap here in the power supply. In other words, not an electrolytic. And then he's feeding into this, on the other side of this, he's putting a 100 microfarad 450 volt Nikon, which is a electrolytic because it shows the symbol for electrolytic. And then that feeds B+ into the rest of your amplifiers. And then it tells you here your 6.3 volt heater winding feeds the 6M1P and your KT88 heaters. And it kind of says here your transformer is has 5 volt, has 375, 0, 375. That nomenclature means that 375 volts here, 375 volts here, 0 volts here. In other words, you could have written that in terms of center tap. And then you've got 6.3 volt winding. So hopefully that makes sense. It's pretty simple. Okay, and one thing I forgot back on example number 3 to mention, because it wasn't drawn straight in line here, but this thing uses basically here a capacitor here. If you'll notice this, you've got a 16 microfarad at 450 volts in parallel with another 16 microfarad at 450 volts. And when you parallel capacitors here, you add them, so 16 and 16 is 32 microfarads at 450 volts. And then it kind of feeds up here and it goes through TR2. Well, this is TR1, which typically stands for transformer, but in this case TR2 happens to be a choke. So you've kind of got C, L, the choke here, and then look, you've got more C here. So you've got a 16 microfarad at 450, and then you're pulling off here some voltage to feed up into the to the output tubes. And then just like we talked about before, you're dropping some voltage across this resistor. You've got another capacitor to even further filter it, so you can feed to your preamp tubes, you know, on up the line here. And last but not least, I'm going to leave you with something pretty cool here. There's something called Duncan's Amp Page, and they have a piece of software called PSU II, Power Supply something Designer 2, and it's a free piece of software. You can go download it on your PC, and what it does is it lets you simulate a power supply circuit. So let me show you that. The software, when you install it and run it, it looks like this. And what you've got up here on the left hand side is a little schematic, kind of physical. You see it represents your transformer here. It represents the two sides of a 5U4 here, and you can double click on this and say, hey, I don't want that to be a 5U4, I want that to be a 5Y3. And you can pick any kind of rectification type you want. You could change it over to be solid state, whatever you want. And you can similarly, you can change the transformer properties. You could change the capacitor properties here. So this thing lets you change. You could add a section. So if you wanted to, instead of CLC, you could make it maybe just an LC circuit or a CRC instead of CLC. You could change this around however you want, and you can change your load resistor. And then once you get it all configured and set up the way you want, you do this thing here called simulate. And when you actually run it, it has ran at this point, and I'm going to read the voltage here across C1, and you can see this is, it shows when this thing is running, your voltage builds up, and then from right here around 400 volts, notice you got all this little zigzag here. And what that's showing is right here, before going through this CLC stage coming off the 5U4, you've got all this noise on top of your DC signal. And check this out. We're going to actually look on top of C2 instead of C1, or actually let's look across R1, the voltage across R1. Look at it, nice and clean. See this green line here? Here, I'll turn off the other one so you can see it. It's a 400 volt signal, nice and clean. If you look at the one with the before it goes through the CLC circuit, you see all this noise on there. Well, that noise would feed right into your tubes, and you would hear every bit of that. And this is probably 120 hertz right here, all this little spikes, because that's what a full wave rectified signal would give you. 120 hertz ripple coming into this capacitor. So between this capacitor, this inductor, and this capacitor, you have basically filtered out all of that. And if you'll notice, you've got a nice clean 400 volt signal to feed back into your amplifier, just like it's shown right here. You feed through this thing, coming out both sides of the 5U4, going into the CLC, and out on the other side comes 400 volts. Just like I showed you here. CLC, got the 375 volts on each side going into this thing, and I had to simulate the load on the output here of 5K, and that got me right at 400 volts. Nice and clean, cool tool. You could come along and say, I wonder what happens if I change this from a 10 Henry choke, because all I've got laying around is a 2 Henry choke. Well, what does that do at that point? Well, if you'll notice, your voltage dropped down just a little bit, and if you look at that, it's easier to see with that on actually. You have just a little bit of, there we go. You got a little more ripple on that thing. Well, let's say if I said, wow, you know, maybe I've got a 30 Henry choke laying around here. What does that do? Well, looks like a 30 Henry choke would still work okay. Or if you said, I don't have that, I've only got a transformer laying around here that's 400 volts on each side. Well, guess what? All of a sudden you're going to be feeding your amp with 400 and looks like about 25 to 30 volts instead of the 400 volts that you had planned on feeding it. So you'd either have to use some dropping resistors to get that down to 400 volts to feed into your B+, or you could risk running this amp a little hot. So it's a great little tool, just let you play around and simulate circuits or power supply circuits. Hope you guys learned something today. I know it's kind of a long one, but I'm trying to be in depth. I'm trying to be in instructor mode and trying to help you understand this stuff. Please post comments in the comment section, ask questions, let me know if you learned something, and if there's something you want to learn more about. I've been getting a lot of requests about biasing. I'm probably going to do a separate video or two just on what the heck is tube biasing and what does that mean. Thanks again for watching, everybody. Stay tuned. I'll come back next time with some more examples. Try to hit a push-pull amplifier and maybe some preamps, phono stage, some other stuff. Thanks, everybody.